All right. Good morning, good afternoon, ladies and gentlemen. Welcome to another set of tutorials with me, Aubrey. In this lesson, we focus on a very interesting concept. It's called a triangular inequality for finite values. This is we have a finite values, and we are assuming that the inequality still works. Remember, the triangular inequality states that when you have two terms, say you have z1 and z2, when you add them, then get their when you get their positive value, this will always be less than or equal to the sum of the positives. Okay, which is intuitively true, because taking, say for instance, if this z1 was negative, then you add it to this, when you sum it to this, it will affect this value because it will be reduced. But in a case where you have z1 taking the positive, no matter how you add it to everything else, it will still always be positive. So this is intuitively true, but we need to prove this, and we is true for n greater than or equal to 2, because for n equals to 1, we know that we're just going to have z1 modulus less than or equal to z1 modulus, which is still true because we have a less than or equal to sign there. So we're starting from n equals to 2. All right. And how we can start this lesson is by first taking note that the inside here, it is the same thing as sigma zn, and this can be written as sigma modulus of zn. So to better interact with this equation, we can say modulus of sigma n equals, we're starting from 1 to n, of zn. This is less than or equal to the summation from n equals to 1 to n of modulus of zn. Right? So from here we can start. So now we are proving by mathematical induction. We know that it has 3 steps. So according to the condition that we've been given, which is n less than or equal to 2. So we are starting from n equals to 2. So step 1, we need to show that the statement is true for whenever n is equal to 2. So when n is 2, we are going to have sigma n, we are starting from 1 and we are ending from 2, of zn less than or equal to sigma from n equals to 1, we are ending on 2 of zn. Okay, now let's dive deeper. So when n is 1, okay, when n is 1, we're going to have z1. When n is 2, we are going to have z2. So this is where we're going to end. So when n is 1, z1. When n is 2, z2. Same applies here. When n is 1, we're going to have z1. N is 2, we're going to have z2. And unfortunately, that's where we're going to end, because we are saying when n is equal to 2. Okay. Now n, we're going to have z1. When n is 2, we're going to have z2. We close, we're ending at 2. So this is less than or equal to, when n is 1, we're going to have z1 modulus, close, plus when n is 2, we're going to have z2. Remember, sigma signifies summation. So these are the values we're going to have for n equals to 1, n equals to 2. And we see, of course, the statement is true because this is a triangular inequality. So just from the looks of things, the statement is true because this is a triangular inequality. So we're going to say true for n equals to 2. Actually, we're doing 2 n equals to 2 since it's a triangular inequality. Which I'm going to assume you already know how to prove, or rather I'll provide a proof in the next year of the triangular inequality. So now from here we go to step 2, and in step 2 we step 2 replace n with k. This step is just written as for n equals to k, of which it's just an assumption step. So in this step we are assuming that n is equals to k, which is, we are assuming that no matter which value we replace in, the statement will remain the same. So assuming n equals to k, where there is n, we put to have sigma k. Remember there is a k, and we're starting from k equals to 1, then modulus like that, zk less than or equal to sigma from k equals to 1 to k of modulus zk. Like that. So the statement, we assume the statement remains the same since we have not changed anything in the statement. All right, so now we go on in step 3. Now step 3 is where we have a lot of work, because we need to show that the statement will be true for all values of n. All right, so this is the step where we need to show. So 3, we're showing that the statement is true, show that it is true, show that the statement is true for n equals to k plus 1. So this is task in this step.